For anyone joining us for the first time, welcome. PI-CASC is a collaborative partnership between the U.S. Geological Survey and a university consortium comprised of University of Hawaii at Manoa, University of Hawaii at Hilo, and University of Guam. This cooperative center is designed to support sustainability and climate adaptation in communities across the Pacific Islands. PI-CASC provides natural resource managers and cultural stewards in federal, state, and local arenas access to the best science available on climate change and other stressors impacting the region's natural and cultural resources. We emphasize cooperative efforts between researchers and managers, aiming to create actionable science and accessible products to use on real-world problems. This Slice of PI-CASC seminar series provides a platform for sharing ongoing and state-of-the-art climate adaptation research and science to management applications in Hawaii, the U.S. affiliated Pacific Islands, and beyond. As you see, this presentation is being recorded and will be made available on the PI-CASC website under our News and Events tab. We ask that you please keep your microphones on mute during the presentation. Please feel free to leave questions in the chat along the way in the presentation. We will have time for questions following the talk, and we'll also address questions that have come through in the chat at that time. At the conclusion of our seminar, we ask that you please complete our short survey that'll pop up once you log off to help us in planning future PI-CASC seminars. So it's my pleasure to introduce our speaker today, Dr. Ryan Perroy, who will be presenting on Big Island, Big Coastline, generating a shoreline inventory for Hawaii Island to increase resilience in the face of rising sea levels. Dr. Perroy is chair and associate professor in the University of Hawaii at Hilo Department of Geography and Environmental Science, and director of the UH Hilo Spatial Data Analysis and Visualization Research Laboratory. He completed his graduate studies in geography at the University of California, Santa Barbara, fellow Gaucho, glad to hear that, Ryan, and has an undergraduate degree in physics from the College of William and Mary in Virginia, where he was captain of the badminton team. Prior to joining the faculty at UH Hilo, he was an assistant professor in the Department of Geography and Earth Sciences at the University of Wisconsin-La Crosse. Ryan, I'll pass it over to you. The Zoom link is yours, and mahalo to you and our audience for joining us today. Take it away, thanks.
Okay, right on. Thanks very much, Brad. I appreciate that introduction. I appreciate everybody taking some time out of their day to listen to this presentation. So I'm going to go ahead and share screen. Hopefully this will work. Let's see here through the PowerPoint guy. And hopefully you guys can now see the presentation.
I've seen it, Ryan. Looks good. Thanks.
Okay, great. So yeah, anything comes up along the way, just let me know and I can stop and go forward. So great. So yeah, Big Island, Big Coastline. So again, a pleasure to speak with you all today. This is a project that has got a lot of different partners and moving parts. And so, certainly wanted to recognize the different agencies and groups involved, including folks who have been providing funding for the project, PI-CASC and the Hawaii CZM program and NOAA and partners at the Hawaii County Planning Department. So it's been a really good collaboration, a really good effort, and I've been enjoying it. And lots of folks to acknowledge from my lab, Esther and Aloha and Naya and Erica and Hannah, along with Stephen Colbert from UH Hilo Marine Science, and a host of other folks who have been, important parts of this and kind of getting off the ground. This is a project that we're kind of in the midst of. So I'll be able to share some preliminary results, but we're not quite done in what we're trying to accomplish yet. It's going to be a busy summer. So I'm speaking to you all from Hawaii, from Hawaii Island, Big Island. It's a beautiful day here in Hilo, and I'm actually on campus at UH Hilo in my office at work, yeah, happy to be here. UH Hilo is a small and very diverse institution on the Big Island. If anybody's looking for an undergraduate or graduate degree, it's a great place. You guys should come check us out. It's just a quick plug for UH Hilo. You can go scuba diving. And again, I'm the chair, as was mentioned, of the Department of Geography and Environmental Science. All these photos are pre-COVID photos. We mask up now, but lots of field work, lots of good experiences for our students, and maybe some of the folks on the talk today are pictured here. Yeah, just a great department, and also affiliated with the TCBES master's program here at UH Hilo. So that's a master's of science in tropical conservation biology and environmental science. So yeah, lots of good things happening here at UH Hilo. And yes, I also run the Seisav Lab, and our mission is to apply geospatial tools to environmental problems of local significance. And so that's part of, and to disseminate that knowledge to the larger island community, that's part of, I'm giving the talk. So I'm trying to, share some knowledge. We work on a bunch of different things, including, volcanic eruptions. We've got a great group of staff in the lab, a combination of students and employees, and projects all over, including out in the Marshall Islands. Some fantastic folks out there that we're able to work with, and projects around Hawaii. So the project I'll be talking about a bit today, it partly started in, I had some need to find a current high resolution imagery for the Hawaii Island shoreline. I'm not exactly sure what I was trying to do, but that's what I was looking for. And I was really happy to come across at the Hawaii statewide GIS program, this Hawaii coastal imagery from 2015. And so I was like, oh, this is going to be great. This is, this really, 2 centimeter high resolution imagery. I can use this to look at whatever it was I wanted to look at. This is going to be fantastic. And some of the imagery is beautiful. This is a house. You'll actually see this house a few times in this talk. But this is a place that's unfortunately experiencing some bluff erosion, and maybe not a safe place to raise your family in this house. But this imagery is great. You can see the debris. You can see all kinds of things at the base of the cliff. But in other areas along the coastline, it's maybe not quite as useful, particularly where the coastline has sinuosity. And I think this is in part because the images were collected with a fixed wing airplane, and so it's pretty hard to bank real quick when you're in a fixed wing airplane. And they had some other limitations, couldn't really fly near airports and other things. And so, where the imagery is there, it's really great. It's a great resource, but it's not everywhere that I was interested in seeing. And these images were also collected in 2015. And so this location, which is on the east side of Hawaii Island, I'm not sure if everybody might recognize where this place is. Probably not, but you will in just a little bit. So I hope, we'll see. This place, we can see that there's issues with the existing imagery because it's dated and there's gaps. But there's other issues. And this place has changed quite a bit from 2015. Hopefully what you're seeing here is a video feed from a drone flight that my group did in collaboration with Hawaii County Civil Defense and the USGS during the 2018 Lower East Rift Zone eruption. Those green roofs there in the background, that's the Puna geothermal venture. And this eruption dramatically changed our island. It dramatically changed me. And it really was a striking thing that occurred, and will happen again here on Big Island. But that 2015 imagery, right? This is what the landscape looks like underneath it now. And so again, there's a need to, on an island as dynamic and changing and amazing as Hawaii Island, there's a need for current data sets that are of a useful resolution for different questions, And there's imagery coming in from satellites, and that's fantastic. But there's a lack of really high resolution imagery on a regular basis coming in to our island. And so that's part of what this project is about, to try to address that in our small way. There's a lot of work going on around Hawaii on issues of sea level rise and coastal hazards. Probably the most impressive and the most amount, coming out of, UH Manoa, the Coastal Geology Group, and affiliated partners, Chip Fletcher and other folks there. This is a screenshot from one of their websites, and it shows a Hawaii shoreline study web map. And I just wanted to highlight, those areas outlined in white on this map. Those are places where they've got things going on and projects and such. If you look at Hawaii Island, there's not a lot of active, white dots on there. And so there's, again, a need for, understanding what's happening on our island, here in Big Island, and acquiring some data that can be used for different efforts. So again, that's part of the motivation for this project. There definitely has been work done, including from Chip. This actually, when I had my job interview at UH Hilo, I didn't know anything about Hawaii, and I read this document because I was trying to learn. I was trying to understand Hawaii, and I remember on the airplane I was reading this and trying to cram for my interview and such. And but this was published in 2002, right? So some time has passed, and again, there's also some more recent work that's been done that includes Hawaii Island. And this is a publication from, again, out of UH Manoa, Carl Kim and others, doing an in-vest GIS analysis with existing data, looking at coastal exposure in the Hawaiian Islands. And they have this color scheme and this exposure index and such. So there's definitely, work that's happening and ongoing. And so, we're trying to contribute to that. And one inventory product that does exist that I just want to take a second to acknowledge is work that Jim Jacoby and Warschauer put out in 2017, looking at in coastal areas, impacts of sea level rise on native plant communities and associated cultural sites. So a fantastic resource, GIS layers that go along with this. Really great. This is based on pictometry imagery, which is about 15 centimeters or so, yeah, really great work. There's also existing data. There's existing LiDAR data from U.S. Army Corps of Engineers flights, which were done in, I believe, 2007, 2013. And my understanding is that there's LiDAR acquisition that's happened recently and is being processed and will hopefully be released sometime soon. I'm not exactly sure if this map captures the coverage area, but all these data sets are really great and helpful. And LiDAR has the benefit of being able to go through vegetation and penetrate through vegetation and get to the Earth's surface beneath vegetation, which is something that our current approach that's a limitation of our current approach, which I'll share in a little bit. My group has looked at shoreline change in the past, primarily work that Rose Hart, a former TCBS student, did for her thesis. There's a picture of Rose with the drone over Honolulu Beach Park, getting ready to do some surveying and mapping. And so Rose looked at 3 different sites around Hawaii Island. Hapuna Beach, classic kind of white sand beach that's been really well studied on other islands. But then Honolulu and Kapoho. And Kapoho is the location that's been covered up by the lava, unfortunately. So in Honolulu, and this is again this house that unfortunately is undergoing collapse. And this is a 2015 pictometry imagery you're looking at. Rose did a really nice study looking at a time series analysis of historic air photos. And it's the case of the magically disappearing house, right? So in 1976, 87, 2009, and it just keeps shrinking away, right? So 2015, and eaten back, and then we're into 2017 when Rose is really active and collecting a lot of data. And so from those those air photos and the orthomosaics that Rose generated through her efforts, she was able to generate this figure and see this shoreline retreat over time. And it's not trivial. And so in some cases, about 6 meters of cliff retreat over the 41-year period captured in her imagery time series. Collecting the images using a drone or helicopter, as we'll talk about in a little bit, if you collect images with enough overlap, you're able to, through a process called structure from motion, generate 3-dimensional models of the landscape. And so what I've shown you so far is, these, where's the shoreline, where's the edge of the cliff based on the images. This is a hillshade relief model. It's 3-dimensional data derived from, drone flights in this case. And this is from June of 2017. You keep your eyes on those locations pointed to by the red arrows. In October of 2017, there had been additional collapse. Right. And so it's not just the imagery, but it's the 3-dimensional underlying data that we can use to quantify change over time, in this case, for looking at, a bluff retreat and coastal collapse. I'm going to shift over to her other site, Kapoho, here just for a second. So again, this is showing these red dots are places where photos were collected. There's a lot of overlap between the photos. The blue crosses are places where we collected ground control, and those are important. So this is, we survey in with centimeter or better resolution differential GPS equipment to get at 3-dimensional coordinates of identifiable places in the scene, and then use those to basically register the orthomosaics and the point cloud in a really tight way with low errors. And this is just a little video here showing. And again, this doesn't exist anymore. This is all covered up by meters and meters of lava. But I'm playing this to illustrate a couple things. One is that underneath dense vegetation, we don't have data, right? And so there are these black gaps underneath vegetation canopy or the rooftops or such. But where there's exposed land, it actually does really, really well. And I would argue, and there's been plenty of papers showing that, basically LiDAR equivalent. Where you've got exposed areas. And so, but again, underneath the vegetation, if it's dense enough vegetation, you're not getting any photons shooting through there. And so we just simply have an absence of information beneath the vegetation. So Rose did all kinds of work, and these different sites, flew the drone all over the place, and covered less than 1% of the shoreline of Big Island. And so what she got was great, but it again, more than 99% of the island is unmapped with those techniques. My group has come across this same exact issue in a different realm, and this is a photo I'm showing that we collected on eastern Hawaii Island of Ohia forest, and those red trees you're seeing there are trees which have been expressing symptoms associated with the fungal pathogens that cause rapid Ohia death. And we, started out doing a lot of, drone flights monitoring to try to identify suspect trees in high-value forested areas. This is from La Pahoja Forest Reserve here on Big Island. And, and then unfortunately we see, there's more and more trees, that are expressing these symptoms. And again, from the high resolution imagery, we can see these pretty readily. What you're seeing here is a sequence of maps from 2016 to 2019 that we generated with drone imagery. And there's these small little postage stamp sized areas. But we, the rapid Ohia death, like sea level rise, it's a landscape issue, right? It's a large scape issue. And so we can dramatically increase our coverage area if we jump over from these drones or unoccupied, because there's unoccupied aerial systems to manned aviation. And in time, the drones are going to totally replace manned aviation for aerial survey. I know that, I believe it. But currently, and the drones are getting better and better all the time, but the FAA regulations and some things associated with the drones themselves make it challenging to cover large, long distances. Whereas with manned aviation, you don't have as many, weight restrictions, and you can fly a lot of other places that you can't necessarily get to with the drone if you follow all the rules that you're supposed to. So we developed in collaboration with Hawaii Volcanoes National Park and Volcano Helicopters and R&R Welding here in Hilo, this system. And so this is our imaging system that we mount to the belly of a Hughes helicopter. And we're using consumer grade cameras. There's some Nikon D850s and a whole host of GoPro cameras. We do have an Aplonix inertial measurement unit, differential GPS system. And this system it's been qualified with the Department of Interior Office of Aviation Safety. And so we fly it and we modify it all the time. And the key for this is that hook in that larger image, because we can drop this at any time. And so because it's jettisonable, that gives us some flexibility in how we mount things and what we do on this guy. And so we've used it, and it was developed primarily for rapid ohia death, but we're modifying it for this work on the Shoreline project to map out the 400 plus kilometers of shoreline here on Big Island. So we've mapped good portions of Kauai with this, 56,000 acres. And so we've definitely covered some ground with producing high resolution imagery with this system. And now we're sort of, moving over into the realm of sea level rise for this one. So I wanted to, if I can, and hopefully the sound can come through, play a portion of a video that was produced about some of this work for the COP26. If you all have seen this before, my apologies. But if you haven't, it gives a good opportunity for Bethany and Aloha to talk a little bit about the project. I also talk at the end, but I'll probably stop the video. I'm talking now, so I don't think you also need to see a video of me talking. It's embarrassing anyway. All right, so I'll see if this will. Hopefully, you guys will hear the sound for this one.
Squeezed between our steep volcanic slopes and the rising sea, Hawaii Island's coastal communities are very vulnerable to natural hazards, including earthquakes, hurricanes, tsunamis, coastal erosion, landslides, and high storm events. These natural hazards make Hawaii County one of the most vulnerable counties in the United States. And in some cases, residents have lost their homes due to impacts from sea level rise and climate change. And in other cases, they're having to redevelop and redesign their properties to accommodate for the hazard.
Hawaii Island is extremely different from all the various other islands or moku'us that we have here in Hawaii. We have these sheer, very tall sea cliffs, and we have different geomorphic regimes. And so what we're trying to do is better understand these changes along these coastlines so that we can provide up-to-date data and information to policy and decision makers like the County of Hawaii.
We formed a relationship with the County of Hawaii, University of Hawaii at Hilo, and the Manager Climate Corps of the Pacific Islands Climate Adaptation Science Center to obtain quantifiable data about our shoreline dynamics and changes in order to adapt our shoreline setback policy, which will make our coastal communities much more resilient to climate change impacts.
We've been able to.
All right. So that's a little bit of that kind of introduction to the project, some nice footage, and hear from other folks than me for just a moment there. So for this project, we've got some different goals, primarily to generate the shoreline inventory for the entire coastline of Hawaii Island. And we're doing that by collecting nadir and oblique visible imagery that's less than 3 centimeters in terms of spatial resolution. And we take those images and we process them through photogrammetry and structure from motion to generate orthomosaics and then 3-dimensional data sets that we can use to do additional analyses for change rates and shoreline topologies and other things that I'll be talking about. the idea is to really to kind of supplement and complement other data sets and efforts that are going on, and really to inform policy. Back to this house, this poster child for maybe changing our shoreline setback regulations here on Big Island. The county, planning department's working really hard on, updating these and revising these. But at least in the recent past, if not still currently, the shoreline setback is in some cases, 20 feet, right? And that's probably too close. It should probably be a little bit further away. And so I've been working closely with the county, and they're very interested in this mapping project, again, to help inform things like setback regulations. And so we've chosen 2 priority sites sort of to collect some preliminary data and sort of work through the kinks about this process, and then we're going to be going for the entirety of the Big Island. And so it's on the west side, the Kona area, just south of the old Kona airport, and then on the east side, just north of Hilo town, up past Honolulu. And don't worry about that riparian area there. That's for a different aspect of the project. So these 2 places represent 6-7% of Hawaii Island's coastline. So it's a start. And the basic workflow: we define the study area, we survey and ground control points to help make our data set as tight and good as we can be. We conduct the flight operations, and that's the fun part. Then we process the imagery, do point cloud classification for ground points, and then generate these bare earth digital elevation models. And then the combination of some of these products can be used in different analyses. So I'm going to talk a little bit about the data we've generated so far, and some of the comparisons and the results that we have. So the Honolulu survey area, it's about 7 kilometers, less than 2 centimeter resolution imagery. We've done a couple flights in this area, and we keep kind of modifying the camera setup for oblique and nadir images. These steep cliff sides, it's nice if you get oblique images, but it's a slightly different kind of flying to do that. In order to have our data, again, as kind of, as accurate as possible, we do use ground control points. So these are points that are surveyed in with differential GPS equipment. Here's a photo of Aloha surveying a point. And so we use existing points that should be visible in the imagery that are invariant, not moving around. Another example here, this is from further up the coast. This was a manhole cover that we used and surveyed in on a nice, safe cul-de-sac. This ground control point work, it happens in places that are safe to be. So these ground control points are not being established right on the edge of the cliff, because you might fall off and die. And so that's just, I wanted to acknowledge that. And then on the Kona side, a whole bunch of ground control points. There's another photo. So it's collecting data, and Aloha's there looking off in the distance. Who knows what she's thinking about? I'm not even going to conjecture, but lots of work to collect these data. This was a case where there wasn't a lot of existing visible infrastructure to work with. So we put out these temporary markers, and people left them alone. It was not an issue. They were out not too long. So we do the flight, and we generate imagery, right? And so this is an example of one of the photos that we generated, and you can see that there's this pool, that the corner of the pool is right there. Like, this whole project is like, makes me be like, oh, that doesn't look safe. Like, I just find myself saying that again and again. And again, this is an oblique shot of that same area. So unfortunately, these folks that there's been active a retreat of the cliff top in this area. When we process all the photos to generate orthomosaic and 3-dimensional products, we get these reports out of the software. We use Pix4D for doing this. And if you believe this, at the bottom here, I don't know how well you can see it, but it says, oh, your overall georeferencing errors is a centimeter, right? I do not believe this. I mean, this is very what's the word? Optimistic. I mean, that's what the report tells us, right? So, but is it really 1 centimeter? No, it's not. We've also included some, checkpoints. I feel a little bit more confident about these. And these are, telling us that the vertical air is about 11 centimeters, the horizontal air, 5, 6 centimeters or so. Feeling a bit more confident about these because these were not included in the processing. These are kind of, checkpoints. And we're also doing work with additional GPS surveys and terrestrial laser scans on the ground to really get a better handle on our errors overall. So we're still, pinning this down. And I think these reports are somewhat optimistic, particularly in areas where we don't have a ground control. Things start to kind of drift a little bit. And again, these points are in places where it's safe to collect points. And so those are not on the edge or right on the sheer cliff side, right? So presumably the errors in those locations will be a little bit higher. This is just a movie of me kind of working with the point cloud. And so those green and red dots, those are places where photos were taken. So you can see the individual flight lines. So we didn't just, fly once, like we actually, covered the coast a couple different times. And so that, comes into the time and the cost associated for doing this, but it provides much better data. And so what you're seeing here again is this sort of three-dimensional point cloud representation of this section of the shoreline. And where we got, exposed bare soil areas, like looks great. Where you got moving water waves, it looks crazy, right? But so it's not good for understanding the surface of moving water, but in other locations, it's can be quite useful. And so we take that in, we process the data, we classify out the ground points. This is just sort of a transect. And so the green are ground points and the blue is structures and vegetation and other things. And we use those to generate a bare earth model. So this is the digital surface model. It's the same resolution as the imagery. You can see there's, coconut trees and other things going on here. And then we go through some processing, and Esther Collier, expert in doing this, and end up with a bare earth. So we try to strip away all that vegetation and structures and things and end up with a bare earth digital elevation model. And we coarsen it a bit. So we go, 2 centimeter bare earth doesn't make too much sense. So we drop it to about a 0.5 meter resolution for those pixels. And then we can use this for different things. So we can look at, the tops of the bluffs, the tops of the cliffs. So this is on the Honolulu side. And what you're seeing here, that blue line is based on the digital elevation model and the imagery, where we've been able to very confidently pick out the top of the cliff, like where what is that position, right? As of, August of 2021, when we did these flights. And what you're seeing here is the sort of a hillshade relief digital elevation model underneath it, to give a sense about where those cliff lines are. And then these are some two-dimensional transects, right? And so, we're able to pick that out really nicely. This is a case where there's bare soil, right? There's nothing confounding us. So this is one where, right in the middle of that line, there's this, big, I think it's an ironwood. And as such, again, optical system, we're not dealing with LiDAR at the moment. We choose to basically, instead of interpolating across, we have a certain size threshold that we sort of throw our hands up and say, we're not going to pretend we know exactly what's going on underneath here. So we've got some holes in the products that we generate, but where you don't have a lot of dense vegetation, it works great. This is a shot of that area there, just to give you a sense. This is another section of the Honolulu study area, another oblique image collected from the helicopter. Again, it gives you a lot of information about the geology and some other things. There's the clifftop line, and you can again run transects down here. And these cliffs are somewhat complex, in that it's not just a single, it's not like a cartoon cliff. This is a term I use sometimes. They've got some complexity to them, different steps and shapes. And this one, I wanted to just share this. So this is another section along the shoreline. And what you're seeing here is this two-dimensional transect using our lab's generated half-meter digital elevation bare earth model. This one is the exact same transect line, but it's based on the 3-meter LiDAR-derived digital elevation model that you can get from the coastnoaa.gov site. And that's derived from LiDAR data from 2017 or 2013. Now, those are two different shapes. And it may be because there's been change since 2013 to the present. But I also think what you're seeing there is smoothing associated with the 3-meter pixel size. And so I'm just pointing that out to make sure that when people are using these data sets for different things, that they're using them to make apples to apples comparisons. And I think that the finer resolution imagery allows you to get at some of the details like these cliff profiles, which I think are important. And again, we know that these cliff profiles are active and dynamic. We've looked back in time using historic air photos. These are a bunch of tie points that Aloha and others worked really hard on to register these photos. And this is an area where, again, we can look at it. We've got, looking down from the 2021 imagery, we can say this is the top of the cliff line, interpreting things from our digital elevation models and other things. And then we can look at the air photo from 1976. Right, we can basically, we don't have 3-dimensional data from 1976, but we do have shadows and other things that we can interpret to do our best job of drawing where we think that line would have been. And so this guy's retreated about 5 meters in the time since. So this is, again, another section, 76, 2021, right? And so we can use DSAS and other techniques to get at measurements of cliff top retreat. And I'll just point out that it's variable, right? In some places it's just stable, right? And in other places there have been some pretty aggressive retreat that has happened. And this gives rates, right? But we know that, or I think I know that these things are episodic. And a recent example of that is associated with Hurricane Lane. So if you guys were in Hawaii when Hurricane Lane hit, at least in East Hawaii, it dropped more than 50 inches. There's a lot of rain. My house, there's a lot of rain there. And so we looked at some satellite imagery that bracketed Hurricane Lane. And that's what's seen in this sort of, first one, 11/13/2017. This is before Lane. And then this 9/6/2018, this is just after Lane. You can see that there's been a fair amount of a loss of vegetation. And then this third one is the 2021 imagery, and it's showing that there's been some revegetation in some locations. But we know that, again, these bluffs and shorelines are changing. As on the east side. On the Kona side, it's somewhat of a different story. There's been change, right? But it's mostly change of developers building properties, particularly where you've got volcanic rock. Like that volcanic rock is not changing, but now there's a hell of a lot of houses. This is a place where, again, the volcanic rock shoreline hasn't changed, but they put up seawalls. There are a few places where we do get, in sort of beach environments, where based on the air photos, our best job of trying to identify the water line from some of these different photos, that we do see some places with change. This is always somewhat dangerous because, the timing of the imagery, we know that there are big seasonal changes across the course of a year where the beach gets replenished and then winter storms come and it takes it away. And so the timing of your imagery can play a role in what kind of rates you're showing. Rose Hart's work in Habuna definitely showed that. And I know that, Chip Fletcher's group has seen these types of things as well. So you take these with a grain of salt, but we do see some areas of change on the Kona side, just not nearly as dramatic as what we saw on the east side. I better pick up I don't know if I even can, I'll pick up the pace a little more and get through some of these additional slides. So we've also tried to generate a shoreline typology. So it's a diverse island. We've got these cliffs, we've got beaches, we've got new lava rock being born all the time. And so we're following methods developed in Australia. They've got this really slick Coast Adapt Shoreline Explorer where they use these, they're called Smartlines. And it's basically attributes of a single shoreline, GIS line that represents the coast, and they're segmented where these coastal attributes change. And it allows you to pack a lot of information into a single line. And the information is about landform, so their form and fabric, what's it made out of, what is the form, and then secondarily some additional sort of morphodynamic descriptors like cliff or shore platform or such. So this is an example again from this viewer. So sandy properties. So some are sandy, open shore sandy, sediment backed. Some are inlet sandy shore, sediment backed, and so on, rock backed and such. And again, this is, you've got a single line here. I don't know if you guys can see my cursor, but at the bottom here it says Smartline segments 1, 2, 3, 4. And they change where these additional attributes change. So you've got geology, the intertidal zone, and then the backshore zone, right? And where you go from beach to rocky shore, oh, you're going to have a new segment there that'll be attributed differently, right? And so it's a really, I like this a lot, and we've applied it for our study areas. Our imagery is good enough that we can definitely discriminate between, for example, sand and pebbles. Like we can see that in the imagery, so we can include that in our shoreline typologies. So we've done it for both. This is a Honolulu side as a boring table here with the information, but basically, again, these shoreline segments have this information associated with them. And this is, I think, a really helpful thing to have. And again, this is a place on Honolulu where it goes from sand to pebbles back to sand. This is a table for Honolulu just showing, the percentage of the area. So about, 34% is lava rock and 55% is boulder beach and such. On the Kona side, about 4% in our study area was sandy beach areas. And those are the places that had change, right? The vast majority of it, the lava rock or the boulder beach on top of lava rock, which is about 90%, those were not showing any change whatsoever. So I think this is useful and helpful for us as we sort of think about which areas need more attention and care. We've also tried to do some sea level rise exposure modeling following the work that Dean Gesh and others did in Majuro, where they basically did Monte Carlo simulation modeling using DEMs to get a probabilistic understanding about where you're going to get inundation. So we took the same approach using our data, where you've got the landscape, it's cliffs right down to the beach. You're not going to see too much change as you go higher and higher inundation levels. That's what's shown in the upper part of these figures. It all pretty much looks the same, a little bit different in the lower parts. But if you shift over to Kona side, more low lying, you are starting to see some additional changes as the inundation increases, right? And so again, there are much more sophisticated ways of getting at inundation exposure and such. But just, I think that these digital elevation models can be a useful input. Other groups have, created things like Tetra Tech, and this is hosted on the PAC.io site, the sea level rise exposure area. Interesting layer that exists at these different increments, half foot, 1.1, 2 feet and such. We did a head-to-head comparison at 2 feet. And I'm just going to show a few examples of this from the Kona side. And then I think I'm going to wrap this thing up because I'm talking a lot. So this is our imagery, your 2021 image. And then superimposed on this is, 2 foot sea level rise inundation using our digital elevation model, right? And so this is what it is. And then this is what we say it will look like. And so, it's all the same data set. So, so to some degree, it's not surprising that it matches up pretty well. This is what the Slerexa 3, based on the 3-meter digital elevation model that's been smoothed and some other things happened to it. They're sort of, but it's 2 foot against 2 foot. So it's the same amount of inundation. And you can see, this blocky nature of it comes out. But in general, they agree, they agree pretty well. And then this is just both of them together. There's some places where they, this structure over here, it's saying that it's, a third of it's covered up in the Slerexa, and we're saying that it's pretty well. Anyway, so there's differences, but I think this is a helpful comparison. This is just another site. This is also on the Kona side, and we've got our 2 foot sea level rise, inundation layer here. some of these rocks you're still peeking out and not seeing too much change. And then this is the Slerexa version here, and then both of them together. Now, again, this is actually this place where the beach is, I think is quite interesting. So, is this a real, so again, the Slerexa data is from, at the latest, I think, 2013, right? So it may be that there were some, beach differences that occurred here, and that this is not necessarily, error between the different data sets, but this is actually representing actual, landscape change. But yeah, that's we're doing more of these types of comparisons, and again, trying to better characterize our data sets as we're moving forward. So again, we've mapped maybe 6 or 7%. We got more than 90% to go. It's going to be a big summer. It's going to be a fun summer, I think. And as part of the data validation effort, we are using in the lab, we've got a terrestrial laser scanner, and so this is. There's Aloha and Esther in the distance there, figuring some stuff out to make this thing work. And so comparing our lab-generated LiDAR data with what we're getting from the helicopter, with what we're getting from the Army Corps of Engineers, 2007 or 2013 LiDAR data, and this new LiDAR data that's going to be coming out. I'm excited about that. And we're always also working on the imaging rig itself. So we have a new photogrammetric, I said that wrong, that's fine. Camera, that's sort of a step up from our just consumer grade DSLR cameras. And so excited about integrating that into the rig. And yeah, starting to lose my voice. All right, so with that, I will say mahalo nui. And if there's any questions in the time we have, or I haven't been able to see the chat this whole time, there might be some things in there. And this is my email if you want to get in touch. So thank you very much for the opportunity to present at this slice of PI-CASC. I hope everybody has a great day. That's the end of my talk.
All right, mahalo nui, Dr. Perroy. Please everybody join me in a real or virtual round of applause for Dr. Perroy. Thank you very much. Great presentation, and thanks for leaving us some time for some questions here. We do have a few in the chat, I noticed, and so why don't we, we've got some time left, so why don't we jump into those. I'm scrolling up to see who was first there. Okay, looks like there's a question. First one I see here is from Damian Kennison. And Damian, I'll go ahead and read the question, but if you want to jump in at any point, please do as well. How much of the erosion that you're seeing along those cliffs, I'm assuming that's what he was talking about, is due to human alteration of the landscape, construction, homes, et cetera? Do you have a sense of that?
Yeah, that's a really good question and a really important question. The drainage of what happens when there are big rainfalls like Hurricane Lane, or we get big rainfalls here all the time, right? But how that rain water is able to percolate or not through the soils, and how it is, concentrated together or not based on culverts or rooftops or other different things, I think is a really important part of why some places maybe are experiencing more accelerated and others aren't. But there's also the underlying geology, which is very complicated and requires, again, all of our work's been from the air pretty much, aside from going in the field and ground control points and such. But I think what's really needed to better understand that type of question, which is a really important question, is to get a much more fine-grained handle on the geology of these areas. And Jack Lockwood and some other folks have done some of that kind of piecemeal, but it hasn't been done extensively across the coastline. And I think, but I do think that, human alteration has played a role in at least some of these places, but I can't prove that outright at this point.
Thanks. There's a note from Jojo Tanimoto, interested in knowing if you're looking at the Kauai to Kohala areas along Waikoloa. Is that in your plans?
Yeah, so again, the plans do the whole thing. So we haven't yet, but I think the work that we've done with the county on these two sort of priority areas has kind of really set the stage well for us to kind of hit the gas and hopefully map the rest of it this this summertime. So that's the plan, is to, yeah. And I don't know that everywhere will get the same amount of intense treatment in terms of time series analysis and other stuff. But the idea is that, yeah, we'll do our best to map the whole island.
Great. I see Dean Gesh from U.S. Geological Surveys here and got a question. Wondering if both the nadir and oblique photos are used in the structure for motion processing to make the DEMs.
So in theory, yes. And Esther could probably talk to you a little bit more about that. Again, we're still kind of refining the system, and it's better if it can all happen during the same. It's better for doing that if the image collection can all happen during the same flight. If we break it up into different flights, and this is a flight that's just nadir, and then the next day this is a flight which is just oblique, it's not as good to sort of put it all together. So that's why through the county and other folks, we're changing the rig to add even more cameras onto that thing. So, but also this new image camera that we got allows us to do some rotation and things. So it's yes, the answer is yes, and it works best if it's happening during the same flight.
Ryan, I have a follow-on question, and I might have missed this, but is the helicopter rig, is that also capturing positional data along the way that you use in the orthorectifying?
Yes, so that's got, and in theory, that should be able to work such that we don't even need the ground control. But we found that if we bring the ground control in, our accuracies go way down. But yes, it's got an inertial measurement unit on there, and it's also got for pitch, roll, and yaw, and corrections for those. And then it's also got a differential GPS on that system as well. Great,
great. A question from Mike DeLu. You mentioned using Pix4D for the processing side. What software do you use for the flight planning side of the process?
I'm not trying to be evasive. I'm just trying to sort of think of that. It's a freely available. So if he shoots me an email, I can get that information. I don't know it off the top of my head.
Yeah, fair enough. Okay, let's see here. Got a few more. We got a few minutes left. Don't mind answering a few more, Ryan. Let's see here. From Damien Kennison, are you seeing that are undeveloped areas of the coastline experiencing as much erosion as the developed areas? Are seeing any patterns or things between developed and undeveloped areas?
Yeah, that's another good question. Most of the area on the East Hawaii side that we've imaged is developed, right? And so it's hard to make that comparison at this point. As we expand, there are definitely stretches where there's much less coastal development. So once we get more information, we'll have an easier chance of understanding the answer to that question. That's a really important question.
Mm-hmm. Question from Aloha Kapono, and I had a similar question. She's asking, what proxy do you use to map the shoreline along rocky shorelines? I think you talked about some of the issues with identifying the bluff top, so maybe you could talk a little bit more about that. But I'm wondering if Aloha might be talking about the base of the cliff to the shoreline there also. Are you mapping that?
We haven't explicitly mapped well, I'll take it back. We've done a bit of work mapping out the base of the cliff. There's a USGS developed tool, cliff delineation feature program that we're trying to work with that can help us extract some of these cliff features. For rocky beaches, so the shoreline that we're using as the basis for our typology, right? That's got all these different attributes to say, this is cobbles or this is sand or whatever. The position of that shoreline is based on the elevation, right? And so I believe it's a mean high water elevation line. And so that's what we use. So it's elevation controlled, and then we attribute it based on what we're seeing in the imagery and what we're seeing in the geomorphology behind that and such.
I hope that answered your question, Aloha.
Yeah,
I'm wondering if I might have misinterpreted a little bit. So you said you're doing a mean high water line, or when in the visual imagery, is that like a wet dry line? Are you also?
No, so that's elevation derived, right?
Yeah.
So we use the digital elevation model to basically set, okay, that's the elevation, and then we have our line that goes along that elevation.
Okay.
So
Gotcha.
it's
Thank you.
an elevation derived line.
A few more here. If you still got any, Ryan. Thanks
Yeah,
for bearing with
minutes.
us, Ryan and everybody. Okay. All right. Christopher Dean is wondering if you've done any studies on the Hamakua coast, particularly where they're building the biomass plant Honua Ola at Pepe Keo.
No, we haven't gotten up there yet. But again, the plan is to map the whole thing. So that will be in the purview of what we do map.
Okay. Question about sea level rise projections. Tori Spence, curious to know how the updated timeline for Thwaites Glacier melting affects your strategy when it comes to gathering data and developing models and overall prioritizing and defining critical areas. So yeah, if you look out to the sea level rise projections, you feel a certain urgency to map this, and how are you accounting for that?
Well, I think that, again, I think there's an urgency to map it based on the amount of change that's occurring, right? That's occurring now because of storm events, because of volcanic events, so there's plenty of change that's happening now, and having, high resolution imagery that allows us to, apples to apples compare that and do some calculations. I feel urgency associated with that. I think that the data sets that we generate can be hopefully used by other folks, right? That have more expertise in, very sophisticated sea level rise modeling and other things. But do I feel urgency about, sea level rise? Yes, I do. Is that going to make me make the helicopter go faster? That's a different timeline. So our timeline is more, availability and weather and lighting conditions and other things. And that's actually an interesting thing. So, you want to map in East Hawaii in the morning because you want good sunlight on those bluffs. Because if you wait too long, they're going to be in shadow. And you also want it to be low tide, so you get as much of the land as you can. So, and then it rains all the time, so there's all these sort of pieces to kind of take into account for doing this.
Okay, one more question I think we have time for, then we'll say goodbye. Christopher Dean's wondering if you factor in earthquakes. Have you seen any effects from earthquakes in your analysis on cliffs or otherwise?
Yeah, so the answer is no, but just like we did, the pre and post Hurricane Lane, there's no reason why you couldn't do a pre and post, earthquake. And so that's something that we certainly could do and could look at to how many earthquake triggered, slope failures were there. That would be something that we'd be able to take a look at.
Okay, well, I think we'll end there with your talk and the Q&A. Thank you so much again, Dr. Perroy. Again, a virtual round of applause for you. We appreciate you joining us in the time away from your busy schedule. We hope that, thanks for the great turnout today. We hope that all of you and more will join us at our next slice of PI-CASC seminar on Tuesday, March 1st, where we'll hear from Dr. Casey Bartson from the UH Manoa Botany Department, where she'll share with us on life on the edge, coastal plant resilience under sea level rise in Hawaii. So please look out for email reminders and sign up information for that event coming very soon, or also you're welcome to visit our PI-CASC website anytime for sign up information on that. So again, please take a couple minutes to complete the survey after you log out of Zoom. It'll help us in planning future seminars and guests. And thanks again for joining us. And we look forward to seeing you all again in March. Mahalo.
All right. Well, thanks very much, guys.